All right, Math 8 students, we are starting lesson 10.1, Properties of Dilations. We are continuing our transformational geometry unit and moving into dilations. Now, just a quick kind of way to remember what dilations are in a nutshell. If you think about if you've ever gone to the eye doctor and got your eyes dilated, they put this stuff in your eyes and it makes your pupils get really big, right? So dilation is a change in that size. So it's making something bigger or something smaller. So let's take a look at our essential question, which is how do you describe the properties of dilations? Now remember, when we're talking about properties, we're talking about size, shape, and orientation. So keep those things in mind as we go through our explore activities and our examples. So moving right into our first explore activity, we are exploring dilations. So the mission that places 12 astronauts on the moon was controlled at the Johnson Space Center in Houston. The toy models at the right are scaled-down replicas of the Saturn V rocket that powered the moon flights. Each replica is a transformation called a dilation. Unlike the other transformations you have studied, translations, rotations, and reflections, dilations change the size but not the shape of a figure. So there's one thing right there. Change the size but not the shape. Okay, every dilation has a fixed point called the center of dilation. So these are kind of important things to remember here. Dilation is what we're working with. Center of dilation is an important term to remember. And that is located where the lines connecting corresponding parts of figures intersect. So this would be the center of dilation for these rockets, right? This would be the center of dilation for these two triangles, okay? So moving in to what it's going to ask us to do, triangle R prime, S prime, and T prime, that's this one right here, the green one, is a dilation of right triangles, of the triangle RST. Point C, right here, is the center of dilation. Now, first thing it wants us to do is use a ruler to measure segments CR, CR prime, CS, CS prime, CT, and CT prime. So we are measuring CR, right, here to here, and then CR prime. And then we'll do the same thing for each of these points. Oops, so I gotta grab my ruler up here. Bring it down. And, oops. So each one of these represents a centimeter, so that would be 10 millimeters. So that's 1 centimeter, 2 centimeters, 3, 4, and 5 centimeters. So I can see that line segment C, R prime is 5 centimeters. So I'm going to write that in here. And I can measure CR too, which is halfway, right? So it looks like 0 to 25 millimeters or 2.5 centimeters, because there's 10 millimeters in a centimeter. And then I'm going to find the ratio of CR prime to CR, right? So this is where that ratio practice came in. So that would be 5 divided by 2.5, which is 2. Okay, so now I'm going to do CS, and then CS prime and CS, okay? So CS prime is 4 centimeters. I should put my units on here. And that's a ratio, so I don't need my centimeters there. This is centimeters. And then CS is 2 centimeters. And then my ratio is 4 over 2, right? CS prime over CS. And that would be 2 again. So that's the same ratio here and here. And that's going to tell me the ratio is going to tell me something about the scale of my dilation. Okay, so then I'm going to do CT prime. So I'm going to rotate this again. I look like I've run just about out of room, but I'm going to make an estimation here and say that's about 5.5. Oh, what do you think? 6? That's a centimeter. That's half. A centimeter. That would be half. So that's about 6. So let's go 6 centimeters. And then CT is 3 centimeters. And then the ratio, 6 to 3, is 2, simplified. Okay, so you can notice that my ratios here are all the same. 2, 2, 2. Okay, so write a conjecture based on the ratios in the table. Well, I think that's going to represent my scale and my distances, right? So something along the lines of the ratios are all equal to 2. Which means all my lengths are proportional, right? All my distances from C, my center of dilation, to any of those points are proportional. Okay, so keep that in mind as we go through. We're going to measure and record corresponding side lengths now of the triangles. Okay, so we're going to do R prime, S prime, and then RS. Oh, I need to come up just a little bit here. So R prime, S prime is this one, and then RS is here. So I'm going to take my ruler, spin it around, and I've got R prime, S prime is 2 centimeters. Make sure I put my units down. And then I'm going to slide this here. And RS is 1 centimeter. So we can kind of see that we're getting the same trend here, the same ratios. Because if I have the ratio of 2 over 1, that would be 2, right? 2 divided by 1 is 2. So we could probably kind of predict what's going to happen here, that all of our ratios are going to be 2 again. Okay, but let's go ahead and measure them. So next is S prime, S prime, T prime. Get my ruler, spin it around. I've got 2 centimeters for S prime, T prime. I'm going to guess S, line segment ST, is 1 centimeter, and check that out. It is. And then my ratio is going to be proportional, right? I can see that trend happening, so that's 2. And then my last side length that I need to measure is R prime, T prime, and RT. So I'm going to get my ruler, spin it around here, and let's go ahead and measure this one first. Okay, so we're looking at 2.8, yeah? It's about 2.8, so 2.8 centimeters. Which means if this was half, this would be 1.4, so let's make sure we're correct here. Whoops. Come on, ruler. There we go. And that was about right. There's 1, 2, 3, 4 right there. So this is 1.4 centimeters. And then my ratio, 2.8 over 1.4. 2.8 divided by 1.4 is 2. So all my ratios are the same again. Okay, so if I'm going to make a conjecture, all the ratios are equal. All the ratios equal 2, right? And so this means all the side lengths are proportional. So just to recap here, we've got, when we measured our distance from the center of dilation to our corresponding points, we had distances that were proportional. And then when we measured our side lengths, we had side lengths that were proportional, ratios. Okay, so measure the corresponding angles and describe your results. So I know that since my side lengths are the same and my shape has not changed, so side length's the same and shape has not changed, I actually know that my angles are going to be the same too. So I'm going to explain that. But you could certainly take some time and measure those angles out. But I'm going to say because I know side lengths are proportional, and shape has not changed, because they told us that in the beginning here, remember up here. Dilations change the size but not the shape. So because shape has not changed, I know that my angles are congruent. I know corresponding And congruent means same size, same shape. Right? So for example, angle S and angle S prime are both right triangles, it looks like. They could both be right triangles. Okay. So because the side lengths are proportional and because the shape has not changed, I know that the corresponding angles are congruent. Okay. So what we saw here in dilations is that we can find proportional distances from centers of dilation and proportional measurements of side lengths. So moving on to explore activity 2. Oh, we got a little reflect here. So two figures that have the same shape but different sizes are called similar. Okay? Are triangles RST and R prime S prime T prime similar, or why not? Why or why not? So yes, they are actually similar. And we know that because their corresponding sides are proportional. Okay, so that means that they're not the same length, but they're proportional. So we scaled that triangle proportionally. So we know their corresponding sides are proportional, and their corresponding angles are congruent. Oops, I spelled corresponding wrong. So the shapes are not congruent, the angles are, though. The shapes are similar. So same shape, different size. Same shape, different size equals similar. So make note of that. Same shape. Versus same size, same shape, which is congruent. Okay, so explore activity 2, exploring dilations on a coordinate plane. So in this activity, we're going to explore how, oh, I missed another reflect up there. Compare the orientation of the figure with the orientation of its dilation. The orientation has not changed, so the figure and its dilation have the same orientation. Okay, so if we had to summarize properties of dilations based on what we know so far, we know they are the same shape, different size, and same orientation. So far, this is what we know. Okay, so moving on to explore activity 2. We've finished our reflex. We're going to explore dilations on a coordinate plane. In this activity, we will explore how coordinates of a figure on a coordinate plane are affected by dilation. So we're going to complete the table, record the x and y coordinates of the points in the two figures and the ratios of the x coordinates and y coordinates. Okay, so we've got our A prime, B prime, C prime, D prime, our vertex. So those are our little corners, right? We've got our x and y coordinates. We've got our pre-image here, which is our blue one, right? So in this case, the dilation made it smaller, right? Our dilation is smaller than our pre-image. And then we got to find our ratios. Okay, so A prime is right here, and so our coordinate is -1, and it looks like 1, 2.5, right? -1 and 2.5. Okay, B prime right here is 2 and 1. Excuse me. C prime down here is 2 and -2. Now make sure you're putting the correct coordinates in the proper spots, right? Make sure you're putting your x and your x coordinate and your y coordinate. That's a pretty common error we don't want to make because it makes a big difference. D is -2 and -2. Okay, now we're going to find our pre-image coordinates for our quadrilateral. We've got A, our coordinate is 2 and 5. B, 1, 2, 3, 4, and 2. C down here, which is 4 and 4. And D, which is -4 and -4. So this is where we're going with this next, but you can probably see that these are proportional here. So if we look at the ratio of our x-coordinates, we've got -1. Oh, this is -2, isn't it? Yep. -1 and -2. -1 divided by -2. I don't know where I got plus. This is a division symbol here. Can you guys see that? We get a ratio of 0.5 or 1/2, right? So for these shapes to be proportional, these ratios should be the same. So that's what we're going through and we're checking here. We've got our prime, b prime, which is 2, over b, which is 4. So 2 divided by 4, and we've got 0.5 or 1/2, same thing. Then we've got 2 divided by 4, again, and we've got 1/2. And then we've got -2 divided by -4. Negative divided by negative is a positive. So this is 0.5 again. So far, all of our x-coordinates are proportional, right? Now let's take a look at our y-coordinates. So we've got 2.5 divided by 5, and that gives us 0.5 or 1/2, same thing. We've got 1 divided by 2, and I'm just pulling these from the table, right? So I've got 1 divided by 2, which is 1/2. I've got -2 divided by 4, and that is actually -4, right? Yeah, that's -4. No, not that one. Whoops, let's go back. This is -4. So I've got -2 divided by -4, and that is 5. And then my last one, I've got -2 divided by -4 again. And that is 0.5. So when I have a coordinate grid, a coordinate plane, I can see that my coordinates are also proportional. So if I look at my ratio here, I've got a common ratio of 0.5 for my x-coordinates and 0.5 for my y-coordinates, which means my points are equal, right? So the ratios, if I make a conjecture here about the ratios of the coordinates of the dilation image to the coordinates of the original figure, I can say that the ratios all equal 0.5 or 1/2.
Just a quick reminder, there is a huddle going on in Mr. Miley's room, so if you run that email, show up.
So ratios all equal 0.5, which means the ratios are proportional. Okay, so if I summarize what we have explored so far, what we're looking at is we have proportional side lengths, we have proportional distances from center of dilation, and we have proportional ratios of coordinates. So big thing is that dilation should be proportional, right? So in Explore Activity 1, we've got our little reflect here. Triangle R prime, S prime, T prime was larger than RST. How is the relationship between the quadrilateral A prime, B prime, C prime, D prime, and quadrilateral A prime, B prime, D prime different? Well, it was smaller, right? So even though it was proportional, right? So it was a dilation, but it was smaller than the quadrilateral. So we're going to say quad A prime, B prime, C prime, D prime was smaller than quad A, B, C, D. And that's all we're going to say. So finding the scale factor is the last thing that we're looking at. As you have seen in the two activities, a dilation can produce a larger figure, an enlargement, so another key term here, or a smaller figure, a reduction. So another vocab word there. The scale factor describes how much the figure is enlarged or reduced, and the scale factor is the ratio of the length of the image to its corresponding length on the original figure. Okay, so In Explore Activity 1, the side lengths of triangle RST, R prime, S prime, D prime, were twice the length of the triangle R prime, S prime, T. So the scale factor was 2. That was that ratio that we found, right? That was that ratio. In Explore Activity 2, the side lengths of the quadrilateral A prime, B prime, C prime, D prime were half, right? So that was that 0.5 that we found of the quadrilateral A, B, C, D. So the scale factor was half. So when you find those ratios, that's what's giving you your scale factor. So our last thing here is our example that's going to kind of let us find our scale, walk us through finding our scale factor. So an art supply store sells several sizes of drawing triangles. That's like these right here. All are dilations of a single basic triangle. The basic triangle and one of its dilations are shown on the grid. Find the scale factor of the dilation. So we're going to use the coordinates to find the lengths of the sides for each triangle. So if I'm finding AC, right, that's 2 units, which is what they did here, 2. And CB, that's 3 units, so that's what they did here. So AC was 2 units, BC was 3 units. So I'm going to find the corresponding side lengths. A prime, C prime is 4, and C prime, B prime is 6. Now I'm going to find the ratios, okay? So I've got AC, which is 2, and A prime, C prime, which is 4. And I'm going to divide my dilation by my original. So 4 divided by 2 is 2. So that's my proportion there, my ratio. And then I'm going to do the same thing for C prime, B prime, and divide it by the original. So 6 divided by 3 is 2. So my scale factor of the dilation is 2. Okay? So since the scale factor is the same for all corresponding sides, you can record just 2 pairs of side lengths. You don't need to do all of them, but you can use 1 pair as a check on the other, right? So you, in theory, if your shapes are truly similar, you should just be able to do 1 side to find the ratio, but we do 2 so that we've got a double check, right? Because if you make an error on the first one, then you're going to catch that with the second one, hopefully. So in our reflection here, the dilation is an enlargement, or is this dilation an enlargement or a reduction? This is an enlargement. We can just look at it and tell, but we can also, if we were just given a scale factor, it's larger than 1, right? So if you have a scale factor that's larger than 1, it's an enlargement. Right? Scale factors. I should say greater than 1, are enlargements. Whereas scale factors less than 1 are reductions. Right, so that's good to know, right? If it's greater than 1, it's an enlargement. If it's less than 1, it's a reduction. Okay, so the last thing that you guys need to do is take a look at your turn on page, what page is this? 318, okay? So I need you to do number 5 right here, your turn, on your own, and we'll go over it in class tomorrow. Okay, so find the scale factor of the dilation. So if you're confused, look back at what we just did in that example to find the scale factor. Okay, I'd also like you to just think about this here, this math talk question. Which scale factors lead to enlargements? Which scale factors lead to reductions? Because we kind of just talked about that in that last example too. All right. Okay, so that's what you guys need to do for class tomorrow. Is that your turn? And then we will go through the guided practice together just as a quick review, and then you'll be on your own. All right. That's all I've got for you guys. We'll see you in class.